This plot illustrates the comparison of three different probability distributions, which is the normal distribution, uniform distribution, and Laplace distribution, and each of them adjusted to have a similar variance. The first one is normal distribution. It peaking at the mean and tapering off symmetrically on both sides, so it encapsulates the most uncertainty among the distribution as shown, as it doesn't perform any particular set of outcomes within its range more than the others, except near the mean. The second one is uniform distribution, which provides equal probability across its range, but with sharp cutoffs. It implies a very different kind of uncertainty, which suggesting complete ignorance about likely values within the specific range, which making it all outcomes equal likely within this range, but impossible outside of it. And the third one is Laplace distribution, which shows a sharper peak at the mean and heavier tails than the normal distribution. So this suggests that the outcomes close to the mean are very likely, but also allows for non-negligible probability of the extreme values. These implications for choosing a distribution is maximum uncertainty principle, which is among all distributions with the same variance, the normal distribution maximum entropy, which is a measure of uncertainty. This means it employs the least amount of the structure and prior knowledge about the underlying process generating the data. The applicability is you have no specific information that suggests another distribution is more appropriate for choosing a normal distribution. It is often reasonable default because it assumes only the mean and the variance of data and the maximum the certainty about the aspect of this distribution. So this normal distribution's property of maximizing uncertainty makes it an effective default choice in many statistic modeling scenarios, especially when prior information about the data distribution is lacking or when data is known to be result of many independent effects. As suggested by the central limit theorem, this explains its prevalence used across various fields and applications, which modeling a wide range of phenomena in nature and society. This plot illustrates the normal distribution, which specifically modeling the human height data for one gender, and this distribution is centered around the mean, which is height of 175 cm and with a standard deviation of 7 cm. So the mean mu is the peak of this distribution. Here is at 175 cm, which indicates the average height, and the standard deviation sigma determines the spread of this distribution. Here it is 7 cm, which indicating how much the height varies around the mean. Let's look at the coverage under the curve. So 68% of the data is within one standard deviation sigma from the mean. This area covers heights from 168 cm to 182 cm, and they are 95% of the data fall within 2 standard deviation 2 sigma from the mean. This area extending from 161 cm to 189 cm, and there are approximately 99.7% of the data is within the 3 standard deviations 3 sigma from the mean. Its range spans from 155 cm to 196 cm. This depiction of the normal distribution is crucial for us to understand how data points like human heights are distributed around a central value, and in many natural phenomena, it allows us to infer the probability of certain measurements occurring within these ranges and to apply statistical methods to analyze and interpret the data effectively. This plot demonstrates the characteristic of the normal distribution, which is focusing on how the probability density change from center towards the tails. And this distribution reaches its highest point at the mean, which is 175 cm at this example, which indicating that these values near the mean are the most probable. As we move away from the mean towards the smaller and larger values, the probability density decreases symmetrically in both directions. So this decade illustrate the extreme value, which is either very small or very large, are less likely to occur. So this symmetry increase to peak and then decrease, which gives us the normal distribution. So its characteristic bowl shape. This is the central limit theorem, which provides a mathematical justification for widespread prevalence of the normal distribution in the natural phenomena and statistic applications. It states that this distribution of the sum or average of a large number of independent, which identically distributed variables, regardless of the original distribution, will approximate a normal distribution. So this theorem explains why normal distribution is so common in statistic analysis, which included those involving human characteristics like height, while many small independent factors contribute to the final measurement.